Come on in, there's plenty of space.
Sorry, 2:50. I'm on West Coast time.
Oh, yeah, okay. Yeah, we'll get going anyways. Open source, right? We can look at, in some cases, the full history of decisions that people have made. You can look at the documentations or the output of it, and you can see the actual implementations. The issue is that with a lot of systems that sort of we are able to see, they're built in a way that's meant to be packaged and sort of easily deployed. And that doesn't fit with sort of a system of multiple services that I tend to build at least. But Kubernetes is a good example of something that is sort of built as a collection of services. So hi, I'm James. I'm the technical lead at Developer Services for your own products. You can come and say hi at our booth. But anyways, so thinking about Kubernetes, was everyone here this morning to see Joe's talk? We'll assume yes and skip the description of what Kubernetes is and talk about sort of why it's interesting to look at. And the main thing is sort of that extensibility piece of it, which leads to a system that sort of has well-defined architectural boundaries and sort of discrete components that make it very interesting to sort of see the decisions that were made around this. So, this is the control plane of Kubernetes, right? This is the bit that sort of runs as your leader. And we have storage in etcd and our API server for sort of validating objects that come in, run permission checks, and eventually store them in etcd. We have a controller manager, which sort of runs a bunch of the baked-in controllers sort of as a single package, and the scheduler, of course, which takes care of sort of placing pods on nodes. And then we have our clients like kubectl or some other API clients, and notionally the scheduler is responsible for putting pods on kubelets. But you're also able to, because of this extensibility, run your own controller or install vendor controllers like Istio comes with a controller. But today we're going to look just at the API server, which is sort of the central piece in the whole architecture. And eventually we'll get back around to the title of the talk. But first we're going to start with the client API piece. So the client API is looking at taking a number of inputs from multiple clients and validating them and eventually persisting them in the API server. And its big sort of concern is, how do we deal with collisions on like concurrent requests? And there's a sort of a number of strategies that are in place there to help with this. The first one is sort of your classic compare and swap, right? So every object that exists in the API server has a resource version stored on it, which is just an opaque field that you as a client shouldn't really care about as long as you always use the same value that was given to you. So if you're going to modify something that exists already, you fetch the existing version, you make your changes, and then you post that back or put that back up, and the API server will ensure that whatever resource version you send up is sort of the same one that's already in the system, and if not, it's going to reject your request. So that way, you can ensure that there's a linear series of requests or of changes, and that whatever the client has thought that it's modifying is actually what it's modifying. Which is good if you want to ensure that the client is going to make a complete change and it says, I'm going to completely modify the whole state of the system or of the resource that it's modifying. But you might also be interested in just making a singular change, right? Just changing the number of replicas in a replica set. So for patching, there's a number of different methods that you can use to sort of describe a patch in an API. And a good one that's implemented in Kubernetes is a JSON merge patch. You can check out the RFC. But it's just a regular old JSON document that is only what's modified in the resource or object that you're changing. So quick example, right? Here's a snippet of a pod definition. in YAML. And if we wanted to modify the labels and also add an additional container, right, we'd send up this kind of patch. So we'd send, an additional, modify the service label and then sort of add this additional container on there. And then what we get out of this, though, is good and bad. You're able to modify objects, but in the case of arrays, a merge patch will always completely replace the value. So what we wish to sort of append, it's always going to be a replace for an array. And that's just sort of ingrained in merge patch itself. So just a reiteration of that. In some cases, you might not want to merge the objects. You might want to actually replace entirely like all the sets of labels. And there's no explicit null either. To unset a value, you would send a null there. So if you actually wanted to say that a value was null, you're not really able to. An alternative is regular JSON patch, which is very verbose, but featureful in that you describe all the operations and sort of coordinates of every specific thing you want to modify. But in Kubernetes, they have a strategic merge patch, which is a addition to JSON merge patch, and it adds directives for replacing, merging, deleting in objects and arrays. And it adds merge keys. So in arrays, like if you wanted to change the version of an image, you could actually maintain the same name and just sort of bump the version. The defaults for these directives are defined in the schema of the resources themselves, and then the client is able to override. So going back to our example, if we did just want to do that actual addition of this sort of sidecar container, the patch looks like what you'd sort of think it should be, and that comes out right because the schema for this container field says that that you're doing a merge on the values. So it's awesome. There's also directives to sort of override these, right? So this $patch value here would let you replace, and if you did actually want to, you could override everything. There's this cool thing, last applied configuration, that is set when you use kubectl apply, and it appends the state of the YAML manifest that you sent up into the object. And this gives a rich context for actually doing these modifications. So if you only care about what you changed last and not what other controllers have changed, you're able to sort of examine that value into it. So the client API, or the design around this, is sort of to preserve the intent of every client, to make sure that whatever the client has tried to do is what gets done, or just don't do it. All right, so onto the internal model, which is where we talk about the controllers that speak with the API server, and back to sort of the title of this talk. So the important thing here is all of these controllers are primarily sort of subscribed to change, within the API server. And so the concern is to make sure that if there's a drop in data, loss in data, or a drop in connection, that eventually the system can sort of return itself to the proper state. So this is where this concept of level triggering comes in, and it's talked about a lot within Kubernetes as sort of a design philosophy, and it comes from electrical engineering or systems programming, where you're actually dealing with electrical signals, or you're dealing with a stream of binary data. And in an edge-triggered system, you're interested in the actual event, like that point at which the change happens. So when a rise happens or when a fall happens. But in a level-triggered system, you're not so much interested in the point of change, but in the state that is sort of the system is resting in. So when you begin to apply this to an actual computer system, the software system, you take this edge trigger concept and you're looking at not only when things happen, but specifically what happened. So you're sending it when this event happens, and you're sending the data that actually changed. In a level triggered system, you are dealing with the full state. So if you change the number of replicas in an edge triggered system, you'd say, hey, add 2 more replicas. But in a level triggered system, you just say the number of replicas is 3. Now it's 5. Now it's back down to 3 again. Looking at it like that, there's an edge triggered system is only sending data when it's modified, and it's only sending the data that has been modified and when it's been modified, the actual change that's happening. Whereas a level triggered system is sending everything, and depending on the sample rate, it's sending it all the time. So, just looking at it at that level, an edge triggered system seems like it would be much better, particularly for network traffic. But there are a number of issues with this that you would have to work around. So this is just sort of going over, what the state is and when the data is sent, that I have already breezed through. But let's talk about some of these issues. So the first one is lost data. So in an edge-triggered system, if we have this rise and fall and rise again, and we actually lose we have a network outage that is coincidentally right at the point of these changes in the data, the only thing that our observer or our controller would see is that sort of final change. And so it would miss that original, up and down value. And it does finally, resync back to the correct state, but it's missed a change in the meantime. With a level triggered system, depending on your sample rate, you have something that is much closer to the actual state of the system. So if you're able to afford, a high sample rate and this bandwidth that you need to use, you can have a clearer view of the actual state of the system, which means that the controllers that are trying to take a replica set and convert it into pods are doing so much more responsibly in the case of failures of transmission of data. So what else can go wrong? Even worse with an edge-triggered system is if we lose that single fall there. So we only observe 2 rises. If we're dealing with an analog system or something like the number of replicas that are running, and each rise here is just add 1 replica, well, we're going to end up in a state in the end where we think there's supposed to be 2 replicas running when there's only supposed to be 1. So our perception of the actual system has gotten out of sync. And this isn't an issue with a level triggered system, because we're always just saying this is what the state of the system should be. We're not expecting the observer to actually do any sort of computations on this and sort of figure out from what it was what it should be. So another issue, slow reactions. If we are, again, talking about sort of increasing the number of replicas, you've got 1 running, and then you go and run a queue control and bump it up to 5, and then think, oh, that's too many, and take it back down to 2. It takes time to increase the number of running pods, especially if you're using some other sort of setup where you may want to do like a graceful sort of ramp up. So it's taking time where you're stepping through things, and you've got the actual state where you're going from 1 to 2 to 3, and then sort of your target in the future, and then adjusting that target as you go. When you're edge triggered, you're just looking at the changes, the additions and subtractions to the number of running values, and it's easy to get completely out of sync here and go way off down to 0 or some value that was never intended to be hit. For level triggering, we're again talking just about the absolute value. So we can see that we're requesting to go to 5, and we start working our way up there. We've reached, say, 3 running, and then there's a new, we synchronize or observe the state again and see that it's gone down to 2. But it doesn't matter that the difference from sort of the chosen state and the new chosen state is larger than we actually have, because we're just sort of adjusting to the absolute value of it. So what are the kind of things that you can build into a system to actually help with these? So for lost intermediate data, like in the case where you're losing a single fall or rise or whatever, in edge triggered system, you kind of need to keep track of what you've seen already, right? And one way to do this is to say, if the system provides sort of a monotonically increasing value for sort of every change on a specific object, then you can look at this and you can say, all right, I'm going to track every revision number sort of in my observer or my controller, and anytime I see one that's sort of higher than I expect it should be, I know that I've gotten out of sync, I've missed some value, so I can do something to perform a resync with the with the canonical source of data. But this isn't an issue for a level triggered system, because this resync is sort of implicit in the design of it. So with stale data, the idea that you're not sure if there's no data, if there's no change in the state, or if you're actually missing the information, you need some way to sort of figure this out. And one option is to run a heartbeat from the upstream system to just sort of say periodically, there's been no change, there's been no change, there's been no change. Or you can just periodically just resynchronize the state and not actually care if you've lost your connection or if you have, or if there's just no change, right? So if you just ask for it again and it's the same, then it's fine. But if it has changed, then you've gotten the new data and everything's good too. So for the slow reaction case, this is where things get a little more tricky, right? Because you need to know in an edge triggered system, you've got to rebuild that state. So you need to say, okay, what was the actual last value that was sent to me, and how did I sort of compute it into an absolute state, and compare that with sort of the real thing that I'm affecting, or the other system, the number of pods or whatever, and sort of recompute the change in state. Again, this isn't an issue for a level triggered system because we're just moving between absolutes. So this is sort of where the famous Kubernetes reconciliation loop comes in. Because the system is level triggered, you are not really caring about having to track any existing state in the objects that you're observing, and you're just sort of looking at what you might be affecting, and you're waiting for changes on this sort of upstream object and comparing it with what you might affect, and then reconciling and working out the differences. So what does this mean for controllers or the consumer logic here? It's just keeping it simple. It may end up that there's extra traffic on the network. If you're resyncing when everything's a-okay, these are sort of wasted transfers and wasted computation. But the logic to do this, to resynchronize after a network failure, is the same thing that you'd have to do when you initially start the system up in the first place. You'd say, give me the state of all these things that I care about. It's just the same as doing that after you think you may have lost the connection. And it doesn't force a consumer to keep track of that upstream state locally unless it wants to. So if you need to do some sort of advanced comparison between how things were and how they now are, well, you can track state. But if you don't need to, if you're just looking at it and taking this replica set and creating a number of pods from it, then you don't have to worry about what the replica set was at before. So putting these together, controllers are clients, right? So the majority of actions that you may be doing against the system is sort of from your just pure clients, but in this case, there's some clients within the system, that are observing the state and then modifying other states or the same one. And it's kind of nice because this resource version that is used for the compare and swap is also used for performing a watch on resources. So it serves double duty, right? It's a value that sort of indicates a point in time on a resource, and you can use that both for saying, has this changed, or for saying, show me everything that's changed since that point. And the same mechanics are used for lists of resources too. So if you asked for all of the replica sets, that has a resource version as well. And then you can just subscribe to change on that, and it all gets sort of aggregated up into this list call. This last applied configuration notion is nothing special. You could implement it in your own controller, any controller could, and care about the specific things that they're targeting and what they had changed last. So in some ways you can actually sort of offload state, if you needed some local state, back into the upstream resource. And all this sort of wraps up into a modification of the robustness principle, right? The idea that you are supposed to be very specific or conservative in what you send, saying like following the specification to the letter, but in requests that come to you, you can be a little more liberal or lax in it and say, oh, this value is, the definition for this isn't actually defined in the spec, then I'll, allow anything here or whatever. And I'll just sort of be kinder to my clients, but on the other hand, I'll be very specific in what I say as well, so that anyone who's interpreting my messages, if they are strict, they'll be okay. Sort of changing this to what you could see in Kubernetes, it's about being exhaustive in what you send and explicit in what you will receive from others. So everything that gets sent out of the API server to watchers is the full value, right? There's no ambiguity there. You don't have to worry about if you've missed some other message, because you're always getting everything. And clients that are sending data to you must be explicit in what they wish to do. They need to send that resource version if they're trying to do a compare and swap, and make sure that they know that whatever the last value was that they thought it was will be the one that they're modifying. So, wrapping up, these are some sort of general takeaways that I think can be applied, not specific to Kubernetes. And the idea is, one of these is to co-locate complex logic with state. So the API server takes care of doing, like figuring out what should be sent out, right? And it takes care of the complex logic for an observer, for a controller. The controller can be completely stateless and just sort of react to changes. And so all of the actual more complicated logic lives within the API server and next to the state that it deals with. Identify the audience and build for them. There's two different audiences for the API server, right? There's clients that are trying to modify data, and clients that are, the controllers that are sort of listening to this data and reacting to changes. And the differences in sort of the profiles of the APIs for each are pretty drastic, in that one is saying, you are just sending, I'm just sending deltas to me, you're just sending what you want to change. And then the other is saying, I'm just giving you everything all the time. But in both cases, it makes sense for the specific audiences. And make it hard for the audience to fail. So controllers don't have to worry about tracking state. They may have to do extra work to do these resyncs, but because of this, and because like the logic to do a resync after a network disconnection or similar is the same as what you need to do when you initially start up your controller, it simplifies the amount of logic that they have to do, and reduces the number of potential errors. So it makes it much more difficult for them to fail. In the same way, for client requests, it's very difficult to make a request that is, where you're not modifying the data that you thought you were modifying. And that's it. Thank you. 3 minutes. Are there any questions? Oh, okay, thank you very much.